Hello and welcome. On a previous video I was showing how to compile Crystal applications, especially CLIs, targeting different platforms, and I was showing or trying to recreate the work that I did 6 months ago that I used to compile tools or CLIs that I use targeting Mac OS or different distributions of Linux with a lot of portability and independency of what is installed on the target system. And that got some questions, and I wanted to do a quick refresh of how this works, what are the dependencies that are needed, how I work around the loss of the work from the last 6 months that I mentioned before, and also how this potentially could be used to avoid the endless recompiling of other libraries that we use on the development environment, like Amoeba or the CLI for Lucky Framework or other similar tools, Crystal, like developing Crystal, that are endlessly compiling every single time that you install it, right? And just to show you that example, I have here just a hello world example, right? And what I'm going to do is compile that. So I have here my container where I have Crystal and all those things. And what I'm going to do, I'm going to run a command that's going to do the cross-compilation. And the cross-compilation happens using this. You call Crystal build, you pass the cross-compile, the target, and the triplet for the platform, the source files that you want to compile, and the output that's going to be the object file that's going to be generated. So something to note is compilers, like in the case of Crystal, are going to take your source code and turn that into object files, which contains the native code necessary to run on that target platform. In this particular case, I'm targeting 64-bit Linux. And then you're going to call a linker that is going to take those object files and link with the associated libraries. In this particular case, since we wanted to build portable executables, we need to use static libraries of those different libraries, right? So I'm going to do that. Crystal build cross compile. I'm going to pass the target I was mentioning before, 64-bit Linux, and I'm going to indicate muscle as the C library that's going to be used. I'm going to take that hello file and I'm going to call it hello 60-bit Linux, okay? 864, sorry, Linux. And what it's going to do is going to grab all the source code necessary, and it's going to generate the object file, which it did here. And it showed me the linking command that I need to execute. Now, I'm not going to execute this because CC is the native compiler. What I'm going to do, I'm going to use a different compiler. In this case, I'm going to use a64 Linux muscle CC, and I'm going to pass the other aspects of the command as is showing me. And I'm going to pass the linking libraries, not the loading path here that is showing, because I wanted to use the libraries for the environment that I wanted to do. Now, in the Crystal documentation itself, it's mentioned to link against the unwind library, which that's what I'm doing now here, passing that to avoid any potential error caused by that. And it's going to grab all the symbols, all the necessary elements. Now, I'm using SIG, which is another language that has a wrapper for the C compiler, and allows you, and has a really well done cross-compiling toolchain. And I'm using that to target that particular binary. Now, if I do take a look to that, I see my object file, and I see the executable that I just generated. If I do a file to that executable, I see it's a static linked 64 bits executable. And if I do an LLD on that file, I see it's not a dynamic executable. If I run it, I get the hello world. Okay, so that's basically the concept. Now, the libraries that I had to indicate in the command line, the GC for the garbage collector, the event for the live event for the event library, all other libraries that I need to indicate, I need to pass, and those need to be already existing static libraries that contains already object files for that specific platform. So those need to be compiled before. Or needs to be compiled at the moment that I'm going to do. And you can imagine the waste of resources if I need to compile that every single time. 6 months ago, that's what I did. Actually, I compiled every single library that was necessary for the different platforms, and I compiled those from source, using patches to make sure that the things are going to work, patching OpenSSL and a different set of libraries, and that's a lot of time. So what I wanted to show is how I redid 6 months of work. Actually, I built a series of recipes that it takes, since I'm already using Alpine Linux for Muscle and already provides static libraries for certain things. I say why I'm going to recompile libraries that are already provided by them, why I don't download them. And that's what I'm doing. I'm actually downloading the APK, which is the Alpine packages directly from the CDN, and extracting from those the specific files that I need. Now, when I'm targeting Apple and macOS specifically, is the same situation. Why I'm going to compile things from scratch when I can go and use the exactly the same static libraries that I was mentioning, but then grabbing those from Homebrew that I already have. And if you take a look to Homebrew, I found, like, for example, the GC, the garbage collector, they have a recipe. The oldest version supported is Big Sur, which is Darwin 20.0, and that's basically what I'm downloading. If I take a look to here, you see here the sellers, which is here is the SHA of the binaries. I'm downloading those binaries from their GitHub packages. So I'm downloading the blob that corresponds to that, and I'm placing that into yes, I'm placing those into a directory that I'm extracting and then packaging those. Now, what I did is place those in a SDK directory, and I'm building a Docker image or a container image with all those tar files, including the macOS SDK. That you can extract that from the command line tool, from Xcode or things like that. I grab that from the macOS, zip it, and put this in my directory so I can build the containers that I'm showing to you. And then the CC commands that I'm running is actually a wrapper around the sigcc command, and I'm passing the target platform. The loading path for the SDK that I was mentioning is already extracted, and then execute all the other lines of the command that you pass. So I'm going to do exactly the same thing as I did before, but this time I'm going to target macOS. So I'm going to do arch64 apple darwin 20.0, and I'm going to call it hello arm64 macOS. This is going to do the cross-compilation of that. It's going to generate the object file targeting that platform, right? And now I'm going to do the arch64 apple executable that I need to do. And you will notice that the linking libraries are different. Here before was GC and live event, and now it's GC, live event, or iconv as linking libraries. So I'm going to pass the O file, target again. I'm going to call it hello ARM macOS, and I'm going to say -lgc, -l event, -l iconv. This is going to generate an executable, again, targeting macOS. If I do a file on that, it's telling me it's a dynamic link executable. So it's not a 100% static library on it. So what I'm going to do now is copy that hello ARM64 to a Mac Mini. I'm going to paste it in the test apps. And I'm going to take a look here. I see the hello ARM64. I'm going to use the O tool and list all the dependencies, and you see it's dynamic linked to IconB and the C library on Mac. And here, this particular installation is using Darwin 22, but I was targeting to Darwin 2020. So it means that in theory, it should be able to run this. Right? So if I do hello ARM64, it works. So that's pretty much the concept. I already took the liberty to pre-compile the other ones because it takes longer, but you have the Lucky ARM or the Amoeba executable. So if I do Amoeba macOS, it already has all the things, so I can go and do, for example, repos, GitHub, Luis Lavena Radix. And it already tells me all the failures that I had on that project. But I didn't have to compile when I did the reinstallation of that on the other platform. So the benefit here is that most of these projects, like for example, when you install Amoeba, it has a post-install hook that's going to, when you do shard install, it's going to execute it, and it's going to go and compile on every single time. So if you have like 3 or 4 projects that are using Amoeba as a dependency, you need to go and compile it. So what I'm trying to do with this is trying to syndicate everything as binaries that you can go and download, similar to what you do with other Go libraries or with other tools that you can just go and grab the executable and use it directly. Or maybe put that in a Debian package, or like a .dev or RPM for CentOS or whatever is the distribution, and you can get the functionality that you need without having to recompile, because that takes time and it's a waste of resources. So I hope you like it. I'm going to make public these 2 repositories, one that is using the recipes using a Ruby, and the other one is actually wrapping those SDKs or those packages into another container image, allow you extending the other Crystal package that I already built. It's called hydrofoil, and this is going to build on top of that in order to wrap all the tooling necessary to do this cross compilation. So let me know in the comments if you like it, or feel free to send your pull requests or changes to the repository. It's missing some README and things like that, but I'm going to work on that and clear that up. Let me know if you like it, and have fun.